Evet, teşekkür ederim. Alright, so we will be discussing internal model control-based PID design. So that will combine a lot of what we have learned so far, including basically direct synthesis method, direct synthesis plus PADE approximation, plus what is called the IMC architecture. So as you will see in a minute, IMC architecture is a generalization of the output feedback architecture. Okay, so we have in fact a different architecture than the output architecture. Remember, in the classical output feedback based design, we have basically the controller acting on the error signal E with a reference signal given R. So the controller drives the plant and you get an output, and you assume that you basically feed the output back to be compared with the reference. So here the error signal is directly the difference between the reference and the output. Okay, now direct design for this architecture requires that you exactly know what GP is. Okay, so direct synthesis requires to know what a GP is. Okay, so in fact, what you assume as GP has a direct impact on the performance of the controller. If let's say if you have something, your plant is not the same as your estimation of the plant, in that case your performance will basically suffer. Okay, now IMC architecture, which I'm going to sketch in a minute, is basically the generalization of direct design for the case where an approximate model of the plant is available, approximate plant model, rather than the plant model, let's say the ideal plant itself or the model of the plant itself. We will assume that we have essentially an approximation of the plant. Okay, where an approximate plant model is available. Okay, let's call this, in fact, this we will call GP tilde instead of GP. So we will, in this architecture, we will make the distinction between GP, which is the ideal plant model. You can assume this is the actual plant. In fact, none of the models are actually the plant, but you can assume that there is a hypothetical plant model, an ideal plant model GP, but you don't have that. You have GP tilde instead. Okay, so what's going to be the architecture? The resulting architecture is something like this. Resulting architecture. Bu arada arkadaşlar, birinizden rica edeceğim, hani çeyrek kala veya 10 kala gibi beni uyarırsa şeyimizi yapalım, egzersizimizi yapalım, olur mu? So the resulting architecture is something like this. You have again a reference signal. You have still a comparison block. And you still have some kind of an error signal, but you will see that the error signal is actually quite different. So in this case, you have a different controller, because this controller will not be the same controller as the one used in the output feedback architecture. Okay, because of the change in the architecture of the system, any controller that we design here will be different from what we will need for the output feedback architecture up here, right? So we will make that distinction as well. So we get an input signal that is driving the plant, but here the plant will be assumed to be unknown. Okay, we will design not based on GP, but based on GP tilde. Okay, but we still assume that this is driving the actual plant, and we can assume that there is also a disturbance here, which generates the output. Now, how do we feed back the signal as differently from output feedback? What we do is that we assume that the same input also drives the approximate model of the plant, and the output, we can call this the estimated output. The estimated output is then compared with the actual output. Okay, so over here, so we have a approximate plant model. It's used to generate an estimated output. That output is compared with the actual output, and this signal itself, which is y minus y tilde in this case, is actually used to feed back as a feedback. Okay, so you see that this error now is a different error signal than what is in the output feedback architecture. Okay, so in a sense it's a bit more difficult to interpret this error, because you see that it's some strange signal, the difference between the reference signal and the output, the difference of the output from its estimated value. Okay, now remember what we have. Remember in classical output feedback, how do we derive the overall transfer function? What we do is actually we write the error function first, right? We basically start with writing the error over here. It is r minus y, okay, and we have r minus y is equal to let's see, y is equal to gc times gp times the error signal. Okay, so gc times gp times the error signal. So what you get basically, right, so what you get basically is an equation in terms of the error. So what you have is that 1 plus gc gp times the error is equal to the reference signal. So you can find the error signal from here, right? 1 over 1 plus gc gp times the reference signal. And from there you can calculate the output, because it's nothing but gp or gc gp times the error signal. Okay, so you get the output being simply gc gp over 1 plus gc gp times the reference signal. So you can express the output in terms of the input, and you can find the transfer function. Okay, so we will now try to do this for this architecture as well. But remember here that as part of this derivation, we also have u is equal to gc times r minus y. Okay, in let's say output feedback architecture. So it basically shows how the controller comes into play in this particular our original in classical output feedback. Now for IMC architecture, we will do the same. Okay, so we will try to remember the basic question is how can we derive GC star, and how does it relate? How does it relate to GC. Okay, we already said that it's a different controller in this architecture, but one question is, can I derive the controller in the IMC architecture, and is there a way to convert it back to be used in the classical output feedback architecture? Okay, obviously you can also use the IMC architecture, but if you use the IMC architecture, you will not be talking about a PID controller anymore. You are talking about, in that case, a different way of implementing the controller. Okay, so let's derive the closed loop transfer function first. Now we still write the error as r minus, in this case we have y minus y tilde. Okay, and therefore we have u is equal to gc star times r minus y plus y tilde. Okay, we also have obviously y tilde being equal to gp tilde times u, so I can basically write u being equal to gc star r minus y plus gp tilde times u. Okay, so I'm getting closer to expressing everything in terms of u. Okay, so let's further that. U is equal to gc star times r minus gc star times y, and plus obviously gc star times gp times u. Okay, now I have u here and another u term here, so I can group the u terms on the left hand side. 1 minus gc star gp times u. Now that becomes equal to gc star times r minus y. And therefore, I can express u as a function of r minus y as gc star over 1 minus gc star gp, okay, times r minus y. Now think about this. This is the IMC version of u. Okay, remember u is what's going to the plant. Okay, so if you had versus output feedback, if you remember what we derived for the output feedback, we had actually u being equal to gc times r minus y. Okay, so we have the same r minus y difference, but here we have a function of gc star, and over here we have a gc. Okay, so that establishes an equivalence between the controller in the classical output feedback architecture and the controller that is being designed for the IMC architecture. Okay, establishes let's say a correspondence. Let's say a correspondence between the controllers. Overshoot in the writing process, between the controllers in both architectures. To do what? To generate the same input basically to the plant. Okay, so we have gc being equal to gc star over 1 minus gc star gp tilde. And mind you that this only uses the approximate plant model. Okay, so let's say remember this result because we will use it. Okay, why we will use it? Because in the following discussion we will first design gc star by using direct synthesis. And after we have a GC star, we will convert that GC star into GC. And once we have the corresponding GC, we will put it in our classical architecture. And we will see that for certain plant assumptions, that's going to lead into a PID controller. Okay. Now, is there any questions so far?
Hocam bir şey sorabilir miyim ben?
Sure, go ahead.
U'nun derivation'ındaki GP tilde olması gerekmiyor mu?
Bir saniye bakayım. Doğru olabilir. Evet, GP tilde olması gerekiyor. Teşekkür ederim. Başka var mı? Şurada da var aynı hata değil mi? Bir saniye. GP tilde U. Evet, şurada yapmışız hatayı. Tamam.
Tamam hocam, teşekkürler.
Başka soru var mı? Okay. So let's continue. Let's continue to derive. The output as we have done in the classical output feedback architecture. We have the output being equal to the disturbance plus GP times U, and we have derived the U. Now, disturbance is here to remind you that we can also deal with the presence of the disturbance, and we will see what we will do with the disturbance later on. Okay, so D plus our derivation GP GC star over 1 minus GC star GP tilde times R minus Y. Now I start obtaining everything in terms of, you see there is a Y term on the right hand side and another Y term on the left hand side. So if I regroup them together, I have 1 plus GP GC star over 1 minus GC star and GP tilde times Y being equal to D plus this same term here, GP GC star over 1 minus GC star GP tilde times R. Okay. Now if I divide both sides by the coefficient of Y, okay, and I'm going to write that, let me write this again like this. I have in the numerator 1 minus GC star GP tilde plus GP GC star over the denominator 1 minus GC star GP tilde, Y being equal to the same expression. Okay, and then once I make the division, I have the reciprocal of this term. So I have a term which is 1 minus GC star GP tilde over 1 minus GC star GP tilde plus GP GC star times this disturbance plus I have GP GC star, there is a cancellation there, 1 plus GC star GP minus GP tilde times R. Okay, so so this is the typical thing that we can do, right? It's like we obtain two transfer functions because the system is linear. In fact, we can derive these two transfer functions also by killing one of the inputs and deriving the output in terms of the non-zero input. But this is what we have obtained for with respect to the disturbance. And this is the transfer function with respect to the reference. And note, same denominator. So the transient behavior is the same, but the steady state values are different. Typically what's happening is that this kind of feedback architecture drives the effect of the disturbance to 0, while it's driving the response to the reference to 1. Okay, so basically what's happening is that the output converges to the reference, while any effects of the disturbance basically die out with an exponential response. Okay, so the same question remains, right? How can we extract GC star? Okay, so there are a couple of things that we will assume. Okay, what we need to remember is that, first of all, we will use direct synthesis, but we also need to remember that basically poles of GC, poles of the controller GC, hence here GC star, are related to the zeros of GP, hence GP tilde here. Okay, so to prevent the controller, remember what was the problem with the Padé approximation. The Padé approximation is a better way of dealing with the time delay, but one problem is that it necessarily introduces an unstable zero to the open loop plant. Okay, so what happens is that open loop zero of the plant becomes an open loop pole of the controller, resulting in an unstable controller. So to prevent the controller to become unstable, we will make a further assumption. We will basically split GP tilde into basically positive, hence unstable zeros, and negative, hence stable zeros, and use the stable zero part in the design. Okay, in the design. Okay, so what we will do is we will basically express GP tilde as two factors, GP plus and GP minus, where GP plus is basically part of GP with only the unstable zeros. Okay, and I'm gonna break here and we will basically continue after our exercise. Okay. Evet arkadaşlar, şeyimize geçelim. Ben şuradan kaydımızı durdurayım.